All right, welcome to this explainer. Today, we're diving into something that, honestly, it kind of sounds like a typo the first time you read it. We are talking about running a true frontier class AI model, specifically a massive 744 billion parameter model on a totally standard consumer machine with just 25 gigs of RAM. And no, that is absolutely not a mistake. We're looking at an incredible open source project called Calibri, and it pulls off the seemingly impossible through just sheer brilliant software engineering.
Okay, let's dive into this. Normally, to run a model of this absolute magnitude, you'd need a massive, incredibly expensive cluster of H100 GPUs, right? We're talking about server racks that cost literally millions of dollars. But Colibri completely flips this on its head. This project runs on a machine that costs less than a single cooling fan for one of those H100s. We're talking about your standard, everyday consumer setup, just a basic NVMe drive and a really modest amount of RAM. So you're probably wondering, how on earth is this even physically possible?
To unpack all this, we've got a pretty clear roadmap today. First up, we'll look at the tiny engine's immense claim. Second, the disk streaming mixture of experts trick. Then, speculative decoding and caching. Fourth, we'll go over some honest numbers on real hardware. And finally, we'll wrap up with the ecosystem and democratization. So, Section 1, a tiny engine's immense claim. Now, the developer named this project Calibri, which actually translates to hummingbird in several languages, and the source material uses this really beautiful analogy to explain it. It says, the hummingbird weighs a few grams, hovers in place, and visits 1,000 flowers a day. And you know what? This engine is exactly like that. It keeps this absolute giant of a model alive on absolute hummingbird rations. Just 25 gigs of RAM, 12 CPU cores, and, well, a whole lot of patience with your disk drive.
Just looking at the numbers for a second, this thing is a behemoth. 744 billion parameters. That's the actual size of the GLM5.2 model we're dealing with here. To put that into perspective, loading this entire model directly into memory, that would normally require hundreds and hundreds of gigabytes of VRAM. It's this massive, prohibitive barrier that completely locks everyday developers out of experimenting with true frontier models locally. But Calibri? It completely shatters that barrier.
Moving right along to Section 2, the disk streaming MOE check. So, the foundational key to Calibri's whole strategy is the mixture of experts, or MOE architecture. Now, as you know, in a standard dense model, every single parameter fires for every single token it generates. But MOE operates a bit differently. It's more like a giant routing system. For any given token, it only activates a tiny subset of its parameters by dynamically routing to specific experts. So out of that massive 744 billion parameter pool in GLM 5.2, only about 40 billion are actually activated per token. That is the real trick here. And this brilliantly illustrates exactly how they pull it off. Because only a fraction of the model is needed at any one time, Calibri essentially splits the model into two distinct locations. The dense part, so that's your attention mechanisms and shared experts, is kept permanently resident in your computer's RAM. They quantize it down to a format called int4, basically shrinking the mathematical precision to save space, and that takes up just about 9.9 gigabytes. The remaining 21,504 routed experts, they're just left sitting on your NVMe disk. That's a whopping 370 gigabytes of data. So instead of trying to cram all of that into RAM, the engine just streams the specific experts it needs directly from the disk exactly when it needs them, layer by layer, token by token. But here is what makes this even more remarkable. This entire engine is written in just 2,400 lines of pure C code. That's it. Zero dependencies, absolutely no Python bloat at runtime, and get this, no GPU required. It is completely decoupled from those massive clunky frameworks, which makes it hyper-efficient and incredibly lightweight.
All right, Section 3, speculative decoding and caching.
Now, streaming experts directly from a disk obviously creates a massive bottleneck, right? So the developer had to build in some seriously clever software optimizations. They're using native multi-token prediction for speculative decoding, basically drafting several tokens ahead of time. They've got grammar force drafts for when you need strict structured output like JSON. They even use router look ahead, which pre-fetches data from the disk before the CPU even knows it needs it. But honestly, my absolute favorite feature here is the KV cache persistence. This means if you close your chat today and reopen it tomorrow, your conversation reopens warm, instantly. It saves your context right to the disk, meaning zero pre-fill time is required when you resume. It's just brilliant. Now, what's really interesting about this slide is a critical engineering discovery they made about speculative decoding. Look at the massive difference in that draft acceptance rate. Speculative decoding basically works by guessing upcoming tokens to save time. But they found that if they quantized the drafting head of the model down to int4, exactly the same as the rest of the model, the draft acceptance rate completely collapsed to near zero. It essentially made the whole feature useless. Actually, scratch that, worse than useless, because it wasted compute. But by keeping just that specific drafting head at a slightly higher int8 precision, the acceptance rate rockets back up to between 39 and 59%. It's this tiny little tweak in memory management, but it yields up to 2.8 tokens per forward pass. So the crucial point is how this ties into the learning cache. And this is where it gets incredibly clever. Because this engine actually adapts to your specific machine and your unique usage habits. Step 1. The engine records exactly which experts your prompts naturally route to most often. Step 2. The very next time you boot up the engine, it automatically pins those hottest experts right into whatever spare RAM you have available. And step 3, because it's now reading from hyper-fast RAM instead of the disk, the engine performance literally accelerates over time. The more you use Colibri, the faster it gets for your specific workflow. How cool is that? Moving on to Section 4, honest numbers and real hardware. I have to say, the developer's transparency here is just fantastic. They outright state this is not fast. And I appreciate that. But let's look at what's actually happening in the real world. On a basic WSL2 dev box with a slower virtual drive, you're getting about 0.05 to 0.11 tokens per second. But as soon as you scale up the hardware, those numbers jump. A Ryzen 9 with a blazing fast PCIe 5.0 drive pushes it to 0.28 tokens per second. And then, pointing to the Apple M5 Max, utilizing that massive unified memory bandwidth and the metal backend, it hits an incredibly impressive 1.83 tokens per second. I mean, for 744 billion parameter model running locally, that is an absolute triumph. And what this ultimately proves is this really fascinating shift in system physics. On machines with smaller RAM and standard drives, you're dealing with a strict disk bottleneck. The system just maxes out its expert cache and is forced to wait around for those slow reads from the NVMe. But the developer discovered that once your disk speed crosses about 5 gigabytes a second, the physics literally flip. The disk completely stops being the bottleneck, and you hit a compute bottleneck instead. The entire load shifts over to the CPU and the math kernels. Which brings us to Section 5, ecosystem and democratization. Colibri isn't just some isolated terminal experiment. It's genuinely built to plug right into your existing workflows. It features a fully open AI-compatible HTTP API, meaning you can just point your favorite existing AI clients directly at it. Plus, there is a really sleek, community-contributed web interface built in React and TypeScript. It's got native support for Windows 11, so no need to mess around with virtual machines if you don't want to. And hey, if you do happen to have an NVIDIA GPU lying around, there's even an opt-in CUDA backend to pin those hot experts directly into VRAM for even more speed. Ecosystem and democratization continued. Now, because this entire thing is a one-person project built on a pretty modest laptop, there is a direct and urgent call to action for the community right now. The developer really needs help testing the accuracy of the int4 quantization. See, running a full quality benchmark on a 1 gigabyte per second disk takes almost a full day for them. So if you happen to have a faster machine, the code is ready and waiting for you in the repository. Running this benchmark and reporting your numbers is literally the single most valuable thing you could contribute to the project right now. It's just so fascinating to see how the open source community comes together to tackle stuff like this. Which leaves us with one final, kind of mind-bending thought. We have just seen how a clever architecture, aggressive quantization, and some truly brilliant cache engineering can squeeze a frontier AI model onto hardware that frankly has absolutely no business running it. It completely challenges everything we thought we knew about the barrier to entry for top-tier artificial intelligence. So I leave you with this. Knowing that you no longer need a $1 million server rack, what could a 744 billion parameter model do on your machine? Thank you so much for joining me for this explainer, and I highly encourage you to go check out the Colibri repository and try it out for yourself.